Hi guys, sorry I couldn't be in our lesson today. I'm away with the Interscope Athletics team for the Intercool Athletics. So the video is for you guys to go through the slides and look at what we're looking at today, and also it's so that because we're at Interscope Athletics can come back to it and also look at it so they don't miss out on today's lesson. So contribution of energy system to specific activities, which is our last topic for this unit. So let's begin. Alright, at any one time, all the three energy systems will be functioning. So the ATP, CP, the lactic acid, and the oxygen system. At one point in time, all three of these will be working and providing the body with some levels of energy. How much will depend on the intensity of the exercise and the duration of the exercise that will be going through. So if it's a high intensity exercise, then the two anaerobic systems, the ATP-CP system and the lactic acid system would be the dominant energy provider for the performance. But if the intensity is low, it's a long duration type of exercise, then the aerobic system, which is the oxygen system, will be the dominant energy provider for the performance. As you already know, the ATP is already in the body. That is the initial 2 molecules of ATP that is available in the body for this quick burst of explosive effort that is required for the body to initiate the body into the performance. For example, a 100-meter sprinter starting from the blocks. Okay, this ATP is only available for a short amount of time because there's only a little bit of it available, so it lasts up to a maximum of 3 seconds. If the performance is above 3 seconds, so it's between 0 to 10 seconds, the ATP-CP energy system will take over from the 3 seconds mark onwards to provide the body with the energy that is required to complete the performance. If the exercise or the performance requires is up to 2 to 3 minutes, then after that 10 seconds, the anaerobic energy system, which is the lactic acid system, takes over and starts to provide the energy that's required to complete that performance. However, if it is a exercise that requires longer duration, so it is above 3 minutes, then the oxygen system will become after that 3 minutes, the oxygen system will become the dominant energy provider for that performance. So if we were to put this into perspective, if we were to link it with the exercise or activities, we are looking at the following. So the first initial explosive effort that is required, which is fueled by ATP, the initial ATP capacity present in the body, it looks at the quick explosive initiation of that performance. For example, a power lift or a shot put throw or a golf swing. All right, where strength and power is required to get that burst of energy to lift that weight or to throw that shot put or to hit that golf, where the body is stationary and doing nothing from going, being on 0 to quickly putting with the body going through an explosive effort to complete these actions. So the ATP-CP system, what that provides energy is, or what happens to the energy it provides, it tries to sustain or maintain that initial power that the body produces. So that explosive power that is produced by the body to initiate the movement, that power needs to be sustained for a little while longer to complete the action, if it is required. In this case, a 100-meter sprint, for example, or a fast break from a group, say a dog is, for example, chasing you, you need that fast break. Or in football, where an AFL full forward player is doing nothing, and then all of a sudden needs to make a lead to present itself to the midfielders to get a mark in front of goal. All right, so the gun has gone off for the sprint, for example. The gun has gone off. The athlete has completed that initial couple of steps, so the 3 steps to get the body upright and start moving, and the legs moving, and that's the explosive power that is needed. And now we need to sustain that for the rest of, say, 90 meters to complete the 100-meter sprint. So that power that is initiated or generated from the nothing needs to be sustained to complete that performance. In football, I made the example of the AFL footballer, the full forward. So what happens in football is that if you haven't watched it, or if you know, then those who have watched it know, and those who haven't watched it, the full forward is the person who kicks the goal. So he stays there, and there's a defender with him. So say that a team that is going to score, all of a sudden there's a turnover in defense. They lose the ball, then the opposition gets it. The opposition kicks the ball out of their defense to their midfield, where the midfielder gets it, and then the midfielder will kick it in the forward line, where the full forward is present itself, himself or herself, to mark the ball, to have a shot at goal. To do that, the AFL or the full forward will be standing doing nothing, because he's thinking that the ball is at the opposite side, which is his team's defensive line. When the turnover occurs and the ball comes from the midfield, he has to quickly break away from the defender and come and find space to be a target for the midfielder to hit the ball to, or to kick the ball to. Alright, so he's going from doing nothing to quickly bursting energy to present himself or herself for the midfielder to be able to get the ball to him, so he can have a mark and a shot at goal. If our performance requires more than 10 seconds, we need to not just sustain the power, we need to have endurance as well. Muscular endurance, not cardiovascular, where the muscle needs to be contracting, or needs to continue to contract until the performance is complete, or the action is complete. So this is where the lactic acid system starts becoming the dominant energy provider to complete the performance. So for example, a 200 or a 400 meter run, or a 100-meter swim. So we have sustained the power, but now because it is a longer duration, the muscles need to keep contracting. Okay, so muscular endurance is needed. So they can able to perform and complete the performance. If our exercise requires or is a longer duration, so it's above, say, 3 minutes and onwards, then that's where the aerobic endurance is required. So it requires both muscular endurance and cardiovascular endurance to complete the performance or the action or the exercise. So anything above 800 meters or above 3 minutes. Okay, the cardiovascular endurance is required to get oxygen delivered to the working muscles, so then the ATP can be rebuilt, so the body can continuously get energy to complete the performance. Muscular endurance again is needed for the muscles to keep contracting, and so the performance can be completed. Okay, so this is how it all works, from going from ATP all the way down to the oxygen system. Okay, how energy is provided for the body and how much is there to provide for the body depends. Okay. The anaerobic energy systems can provide quick bursts of energy, but unfortunately has a very small amount of it to produce. Whereas the aerobic system, or the oxygen system, can produce energy at a much slower rate, but has an almost unlimited capacity. Okay, so to understand this, we have a graph here to explain it. All right, so if we, sorry, I clicked the slide. Okay, here we go. So we have two bars. Okay, the red bars represent the rate of the energy release, so how quickly energy is released to complete the performance. The blue bars represent the amount of energy released for that action. So as you can see, the ATP-CP system and the lactic acid system, which are the two anaerobic systems, can release energy very quickly. Okay, the red bars. However, there's only a short capacity, or small amounts of energy that they can produce in that quick rate. They can produce it really quickly, but there's only a small amount here. In the ATP, it's very small. You can see, in the ATP-CP system, it's very small. Lactic acid system, a little bit, it can produce a little bit more. Then compare that to the oxygen system that produces lower has a, it produces energy at a very slower rate, but has a lot of energy to produce. Okay. Now, if in the oxygen system there is a bit of a difference. Okay. If we come down here, we have 4 bars. Okay. We have oxygen system where carbohydrate is the main fuel, the main nutrient used to fuel the body. Then we have oxygen system where fat is used as the main nutrient to fuel the body. All right. The reason for that is that once the carbohydrate is exhausted, or there's no all of carbohydrate in the body has been used, then the body goes to fat supplies to burn and to produce energy. Now, carbohydrate can produce energy, okay, at a quicker rate. Okay. Now, the reason for that is, compared to fats, carbs have smaller molecules, so it can be broken down quickly. Whereas fats, it has larger molecules, so there's a lot of work needed. Then that means a lot of oxygen needs to be delivered to the working muscles or to the body to break down those large molecules and produce energy. Because of those large molecules, it takes time to break it down. Whereas carbohydrates, it's smaller molecules, gets broken down quickly. However, fats can produce more amounts of energy compared to carbohydrates. All right, fat, as you know, for 1 gram of fat, 37 kilojoules of energy is produced, compared to carbohydrate, where 1 gram of carbohydrate can only produce 17 kilojoules of energy. All right, so that's why you have a large capacity of energy provided by fat than carbohydrate. So in the past, it was suggested that aerobic energy system, or the oxygen system, can only produce energy, or large amounts of energy, in lower intensity exercises. However, recent evidence suggests that the aerobic energy system can produce at high intensity exercise as well, and can and do it at a greater extent than previously believed. So it is suggested that aerobic, or the oxygen energy system, contributes up to 50% of energy requirement, 50% of energy requirement for a 60-second effort, which is between the ATP and the lactic acid system. So in that time, 50% of energy is produced either by the ATP, CP, or the lactic acid, and the other 50 is produced by the oxygen system. Again, so after just 30 seconds of high intensity or maximal exercise, the oxygen system can be at a high. It could be as high as 30 to 90%. If an athlete has a very large VO2 max, or has a large capacity of oxygen volume that they can inhale. Okay, we will look at that in a graph as well. That is which you will be given, which I have written in here for your relief to have a look at. You can see the lines to suggest that which energy system provides how much energy at one point of time, and when they get used, and when they drop, and when they get at the most dominant. So that is today. In the first 60 seconds, the body will utilize predominantly the ATP-CP system. However, the other two systems will contribute, but not as much. After 60 seconds, the contribution of the ATP system falls significantly, because it is used and replaced by both the lactic acid system and the oxygen system, as I just said. The 200-meter sprint, for example, the intensity is at very maximum. It's a 20-second performance. So if you look at the diagram, you can you see that which system is being the dominant provider of energy. Now, I have a couple of questions attached as well for you to have a look at and answer. So if you have any questions about today's or this unit's about this topic of the unit, please email me and I will try to get back to you. But please have a go at those questions, and we will discuss it when we come back in next lesson. Now, and I will let you know about test as well. So we won't have test. We won't have a test next week, because I'm not here today. But I'll see you in PE and we'll discuss that. All the best. Good luck, guys. Bye.